Like I said, my name is Liz Ward, and this is Troy Lake, and together we are doing the Career Development Seminar Series. I am very privileged and very thankful that Bill Fredericks agreed to talk to us about his experience in breaking barriers inside of a bureaucracy, because that's where we all work, right? Well, work inside a bureaucracy. And he's been very successful, but before that, he was also a student. He started as a co-op from Purdue in 2003. And in 2006, he became a civil servant working for the Systems Analysis and Concepts Directorate. He's worked on like ARES 1, high altitude UAV searching for hurricanes, and truss-braced wings for fuel, right? Something like that. But his favorite project he's going to talk to you about. The other thing I wanted to mention is he is an AIAA committee member for the VTOL committee. So that's pretty significant because that's national, right? And he is a 6-year veteran of the United States Marine Corps. So we applaud you and thank you for your service. And he was deployed to Afghanistan in 2011. He came back alive and came back to NASA. So we're really blessed to have him here. And Bill?
Wonderful. Alrighty, so today we're going to talk about breaking barriers. And these barriers that we see, whether it's a bureaucratic organization with processes or physical barriers that physics you need to overcome, or whether they're interaction barriers with interpersonal skills. Lots of opportunities to extend beyond what is perceived by yourself as a barrier, and I would suggest that the real barrier is a lot farther out than you personally perceive. Oh, of course. Oh, there it goes. So let me first start with, I found this on the internet, and it's a great quote. And actually, I'm also a sailor myself. I've been sailing since I was knee-high to a grasshopper. But, and the quote is, "A smooth sea never made a skilled sailor." And there's lots of forms of this, but if you don't go through something trying, you probably haven't tried. And so being in a difficult situation means a lot for personal growth and development. To use an analogy, when I was in boot camp with the Marine Corps, I went through in wintertime, and every morning we'd run the endurance course, and it's like a 3-mile run, and in one part of it you're going through chest-deep water, and one morning we get up, it's super cold outside, and we show up to the deep water ford, and it's covered in ice, and I'm like, what are we going to do? Well, didn't even stop, kept going, went right into the icy water. It's about 40 yards long, and we're breaking the ice with the butts of our rifles as we're going through this chest-deep water. And the point is, it sounds crazy, it sounds like hazing, and yes, but there was a purpose behind that, and all of us got out of the icy water at the other end. It's totally doable. Your mind thinks, I can only do so much, but in practice, you can go much farther than you really can. And so that's what I want to mention on this slide, is that in the midst of adversity is when you grow. All right, so today I'm going to use an anecdote talking about the Grease Lightning Project, which I'm, who's heard of this and who's not? Let me actually say who's not heard of it. A few, okay. So this was, I'll just give a quick introduction. This study was actually started by an other government agency, and they went to the aerospace primes and said, we want an aircraft that can take off and land vertically and then fly for 24 hours while carrying a 60-pound payload. And they came back with these like massive catapults and like catch nets and stuff. And they're like, no, you don't understand. We want VTOL, like how a helicopter lifts off the ground and then can fly 24 hours. And they said, well, there's the door, get out, it's impossible. So then they came to NASA Langley and to see what the space cadets could come up with. And I was naive enough to say, sure, I'll try it, why not? I mean, the money's here, might as well try it. And so we went through a bunch of designs that, or I'll get into those details in a minute. But in either case, the purpose of this project was to demonstrate feasibility of something that previously was considered impossible. And it wasn't so much to research the exact flying qualities of the vehicle, but it was a proof of demonstration was the purpose of the project. All right, getting in motivation for research. So actually, I already covered this, but They wanted to combine something that can take off and land vertically, like a rotorcraft or a multi-rotor, with the cruise performance of a fixed-wing airplane, like that. This particular aircraft is the Scan Eagle. But you'll notice how it becomes runway independent, has a big old catapult, and I don't know if you can see in the background, there's a crane with the vertical wire, and the way they recover the aircraft is there's hooks on the wingtips, and it has differential GPS, and it flies into that wire, catches it. The problem with this system is it works great, but this ground infrastructure is 20 to 30 times heavier than the aircraft itself. So that makes a huge logistical burden to deploy that system to where you need to go. So can you have just the aircraft take off under its own power and then fly like it's a fixed-wing airplane in terms of cruise performance? So that was the purpose of the study. So we first started in sort of the concepts phase, and these were all paper designs of vehicles we came through, and we did these paper designs and said, sure, try and build something, see what you can come up with. So we built these 3 vehicles, and we splatted all 3 of them, and we decided, you know what? From those lessons learned, let's back off on the aerodynamic performance we're trying to achieve a little bit, and we changed the design completely, and that's the Grease Lightning design that many of you have seen. So this project was on a really tight budget. The total project was done for less than $2 million. And this was starting from a clean sheet of paper all the way to the flight testing. So we didn't have a lot of resources to apply. So we had this airplane called GLARF. I think I said one day, someone just needs to barf me up a few airplanes that we can crash. So this aircraft was our simulation. And this was not a perfect model by any means, but the purpose, we built 5 of them, we crashed 3 of them, and in the process, we're able to get a first estimate of all the feedback closed loop gains to fly this airplane. So it is unstable. This airplane, like a typical airplane, if it disturbs, it'll naturally come back to its flight condition. This aircraft is like an inverted pendulum problem. Well, not exactly, but it's unstable. If you don't do anything, it'll immediately depart out of controlled flight. And we also use this, the GLARFs, to determine the schedule of that wing rotation and the tail rotation. So the first thing you think of, just lock them 1 for 1. But in practice, what would happen was, as you start accelerating forward, the propellers on the wing are turning the flow field, which changes the local angle of attack on the tail. So the actual schedule of the tail rotation was kind of an S-curve. And at the other end, the wing loading is higher than the tail loading. So the wing had to be at a higher angle of attack than the tail was at. So at first, the tail starts rotating quicker, and then they pass each other a little bit, and then the wing has to be at a higher angle than the tail at the last bit of the transition corridor. So that was the other purpose of these vehicles. And the other thing is we bought a commercial off-the-shelf control system off the internet and downloaded open source code. And one of the barriers we ran into was, so you're going to fly an airplane that costs $300,000 to replace on a controller that costs $38 off the internet with open source code you downloaded. And so that was a big barrier. So we had this flight testing campaign with the cheaper vehicles to build confidence in that physical avionics hardware. They were soldered up in China by people that were severely underpaid, so you don't necessarily know if they actually put together a good piece of hardware. And then the software itself, we put version control on the software. We know that this version of the software works and doesn't have bugs in it, and we flew it on this airplane first. And so that particular piece of hardware and that particular version number is what we then took to GL10. Then the purpose of the bigger picture GL10 was to validate this capability at a relevant scale. So the vehicle for the other government agency is actually a 20-foot wingspan, 275-pound aircraft. And they said, okay, build us one of those. And I'm like, sorry, you only gave us $2 million. So we decided to make a half-scale version of it and show that in fact, that you can build a vehicle and you can get it to transition at a relevant scale. So actually, I've seen RC doghouses flying. So if you have sufficiently low wing loading and sufficiently high power to weight ratio, you can make anything fly. So this was done at a relevant scale. So the thrust to weight ratio and the wing loading were not perfect dynamic scales, but they were close to what the actual conceptual design of the real vehicle would be. And also, this is a proof of feasibility for new vertical takeoff and landing markets that could enable many new systems. I'm sure everyone's seen the Amazon package delivery thing. And I don't believe there's any representatives from Amazon, but their current design, their current vehicle doesn't make any economic sense. So the legs that that vehicle has, it can go out about 10 miles and back. So can you imagine Amazon having to build a distribution facility every 10 miles? But if you had a vehicle with performance like this, you could now build one distribution center per metropolitan area, and now that business model starts to make sense of on-demand package delivery. All right, so this is a video, and ooh, it might not play if you're not in presentation. Let's see if I can hit play. So this video is two flights pieced together. This first flight you'll see is vertical takeoff as it lifts off the ground right here. And we're going to rotate into what I call the teeth of the transition corridor with wing and tail angles at approximately 45 degrees. So we tufted the upper surface of the wing, and you'll notice one thing that's interesting is these panels here and here stall before those panels there and there. That's because of the propeller rotation direction. So in this region, the propellers are moving forward. In that region, the propellers are moving aft. So they're turning the flow field more effectively. Here, once we get lined up with the runway, we'll rotate forward into that slow forward flight condition with the wing and the tail at a 45-degree case. Here we go. Now we're rotating. And you'll notice, as we build forward speed, V infinity swamps out the propeller slipstream, and the wing becomes totally stalled. So before we got the feedback gains correct, this vehicle was all over the place. Up on the nose, you see a string. That's our alpha beta vein, our simplified alpha beta vein. No data recording except for the camera. But this vehicle's all over the place. It's doing this nasty backstroke and frequently had to abort back to hover on multiple occasions. Once we finally got the gains close, then we could fly there. Now you'll also notice now we're back into hover, so we just spent about 30 seconds flying around angles of attack of 45 degrees, which is unheard of, with the exception of like the F-22. And the reason for that is the control system at very high frequency is modulating the throttle commands and those control surfaces on the wing to stabilize. So we're getting a lot of lift out of the wing. However, the wing is also making destabilizing yawing moments and rolling moments in an unsteady manner. And the reason why we can overcome it is there's lots of control authority. On the next flight, you'll now see a full transition. And we also started immediately going into that slow forward flight condition just from an operational perspective. We only had 4 minutes of battery on board the airplane for most of these flights, so we wanted to get up and out quickly. So we'd quickly go to this slow forward flight condition, and once we'd climb upwind and turn downwind, and we're 2 mistakes high in altitude, as I learned from the controls folks, then we finished the transition all the way into wingborne flight. Here we are, we're about to accelerate out into fast forward flight. There it goes. And you can hear just the aircraft accelerating, the microphone, getting all the wind noise. And the airflow is now fully attached again. And at this point, it's flying like a normal airplane again. Eventually, 8 of these propellers would all be shut down and folded, and only the 2 wingtip propellers keep operating. So if you consider like the V-22 Osprey, its rotors are compromised between That was a pitch doublet right there, and you'll notice, I'll answer that question in a minute. But how quickly these pitch doublets damp out because there's closed loop controls damping the vehicle. I also made the tails a lot smaller than normal because we needed a control system on it anyway. So the V22, its rotors are a compromise between the hover conditions and the forward flight conditions, and is not near ideal propulsive efficiency at both conditions. So by matching the disc area to the thrust required, you could stay near ideal propulsive efficiency at both cases. So I just did kind of a low pass, just for fun on that particular flight. And in this, I believe on here we should be coming back. There we go, here's the inbound transition again. And as that wing cranks up, the vehicle just slams on the brakes when the airfoil stalls, huge amount of drag. And then here we go, turning on to final. Actually, I think we make, oh, here we go, back into hover. You also notice something interesting here too. Here the airflow is nicely attached. Watch as we get into a very high descent rate. And it's going to come here right there. Notice how the airflow came reverse circulation up from the bottom. So pitch and roll were still stable, but the yaw axis went unstable because you got airflow coming up from the bottom at the same speed as the props blown down. Net effect, no dynamic pressure on those control surfaces, and it just went unstable, only in the yaw axis. So our mitigation to that was just don't do that anymore. So you always keep some forward speed on and hover. And this is one of the more interesting plots. So if you look at like the classic sort of VTOL aircraft transition corridor plots, you have airspeed and wing angle, and actually someone from the XV15 program told me I got my axes backwards. So technically, wing angle or nacelle angle is supposed to be on the y-axis and airspeed on the x-axis, but so be it. And you'll notice all the flights, well, this isn't all the flights. This is like traces of 10 different flights we did. And there's some regions in here that are interesting. So the first point I'll notice is the wing-borne flight stall speed is right here at about, what's that, like 18 meters per second. So if you're below that, you don't have enough lift on the wing. And if you're below this curve, I drew this curve in PowerPoint, so it's close. It's not exactly where that threshold is. If you're below that, your wing is at too low of an angle for that airspeed to support the weight of the vehicle. So you'll notice all these traces here went below, so the vehicle was at less than 1 G. In these cases, it was like at 0.8, 0.9 of a G, but it wasn't steady state, it was accelerating. And if you're above this line, we'll break the wing tilt actuator because there's too much dynamic pressure on it. And if you're above this yellow line, there's insufficient forward axial force to accelerate outbound. And all these traces, they're all the inbound transitions. So here the vehicle's decelerating on those traces. The other thing to get off this plot is basically how we did our envelope expansion. So the first thing we did was we had the GLARFs first. And once we had the GLARFs, we took the big GL10 and did tethered hover testing. So we made sure all of our hover feedback gains were good while we're still belaying the aircraft on a tether. So we didn't have any risk of crashing the vehicle at that point. Once we were comfortable with hover, we took it off the tether. And then we went a little bit into that transition corridor, saw how that point was, came back to hover, landed, made adjustments as necessary, went a little bit farther in the transition corridor. We're checking pitch control authority as well as pitch trim. And once that was good, come back to hover and land, and incrementally expanded the envelope farther until we got to about a 25-degree angle. At that point, we said we'd just push the rest of the way through. Because being in this region is the worst place. You have enough dynamic pressure to get you in trouble, but not enough dynamic pressure to hold the weight of the aircraft up. So we just shot through that last little bit without spending time there. Okay, so takeaways, back to the bigger picture. So when we think about like career development and breaking boundaries, some thoughts that you all should keep with you as you go forward. First one is lead by example. And that applies to your subordinates, your peers, and your superiors. So you can influence your boss, you can influence your peers, you can certainly influence your subordinates. And to use an anecdote, we were in Afghanistan, we were preparing for an attack on Bagram Shah, so I won't go into any of the attack stuff. But preparing for it, we knew that we wanted all the Marines to practice using the crew-served weapons, the big machine guns. And everyone's like a little tense because in 3 days we were going to go. But I knew that we all needed time to practice, like in case you get a jam, disassembling that weapon, putting it back together again. So, and I knew that all of them needed to spend some time doing it. So we had all the corporals teaching classes to review to everyone how to do all this. And what everyone needed is just time practicing. So what I did was, after one of the corporals finished teaching his like 10-minute class, I told him, start your stopwatch, and he hit the go. And I disassembled and reassembled that machine gun in 27 seconds. And I went, holy shit, did you see what the lieutenant did? Oh yeah, sorry, I'm being recorded. But for the next 2 days, nonstop, I couldn't even sleep. You heard bang, 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 bang. Everyone was trying to beat my time on disassembling and reassembling the machine gun, and it took 2 days before someone beat me. But you know what? They spent 2 days practicing how to use that weapon system, and I didn't need to tell anybody, you shall spend 10 minutes doing this the next day. So it's a way to motivate people to do the right. So whether they're your boss or your subordinates, you have to think of what would motivate those people and how to get them to do what they'd want by their own motivation. And even in a combat situation, that's the best way to lead. Another takeaway is, if you don't push to the edge of the envelope, I would say you don't necessarily know where the edge of the envelope is. So as we were first doing the Grease Lightning Flight project, an assumption that I had made is we wanted to keep the wing below stall angle of attack in that transition. So you've got the propeller slipstream always blowing down, and hypothetically there's a trajectory line that you could trace out in a climbing trajectory where the angle of attack of the wing never exceeds the stall angle of attack. And in practice, we found out that just wasn't going to work because the vehicle would have to gain so much altitude it would just be gone and you couldn't fly it anymore because you couldn't see it. So we decided, you know what, and we tried this with the GLARFs first, is we're going to try flying the aircraft beyond stall angle attack of the wing. And it wasn't until we pushed that envelope did we realize that we could actually do it. So if you don't push towards the edge of the envelope and realize that that's now a risky situation you're putting yourself in, you won't necessarily know where that edge is before you lose the vehicle, or think of analogies with personal relationships. And I say that sounds bad, if you push people till they snap at you. But again, the point is, if you don't push towards the edge and make a little bit of a ruckus, you'll never know what the edge is. Another one, never accept no for an answer. And if someone tells you no, the response isn't, okay. The response is, what do I need to show to you for you to say yes? So no matter what the case may be, for example, using this cheap flight controller, people are like, get out of here, it's ridiculous, that's never going to pass ASRB. So then you push back, okay, what would you need to see to know that this piece of hardware and this open source software can fly the airplane? And that's the genesis of why all the GLARFs were built. And we planned on building 5 because we knew we were going to crack some up. And we cracked up 3. There's still 2 left that are in flyable condition. But if someone tells you no, push back and ask, what do you need to see for you to say yes? And that applies to anything, even like getting human capital forms approved and things like that, whatever the case may be. The other thing is persistence. If you want to accomplish something of value, I would argue that it's not going to be easy because it already would have been accomplished. So as you come up to roadblocks, you need to be persistent. So if you still have the means to keep going, there's no point in stopping. So being persistent, if you hit a roadblock, find a way to get around it and keep going again, being persistent. Another big takeaway is willingness to accept risks. So one of the things that was unique about this Grease Lightning project is our research question wasn't so much the value of the vehicle itself, but a proof of feasibility. And so with that research question being only a proof of feasibility, we could get buy-in from management that, hey, we're going to accept risk, because if we don't try and push the edge, we won't necessarily, basically, if we didn't fly the vehicle, we would have been unsuccessful as a starter. So being able to accept risk and being upfront with management to say, hey, this is what I want to do. Let's be realistic. We're likely going to crash or fail or whatever that may be. But you need to manage stakeholder expectations to make sure that they understand that this is going to be risky and we're going to do X, Y, and Z in order to show this. And when you crash it, you've already managed your stakeholder expectations to realize that, hey, they had input in at the beginning to accept that risk. Versus the bad thing to do is to go off rogue and be like, hey, I'm going to do it, and you crash it, boom, it's done. And everyone's like, wait a minute, why'd you do that? You have to manage the expectations up front before taking those risks to get their buy-in. And the last one is stay positive. Like, for example, like getting assistance with the Aviation Safety Review Board. Keeping a positive attitude towards them and saying, okay, yes, and what can I do this? And keeping positive and keeping persistent. If they realize that, okay, you're not just going to go away and you're being positive and trying to be helpful, they will, people will help you. Because everyone has a good-natured heart. Well, maybe not everyone, but most people have a good-natured heart. And if you stay positive and you're not like insulting to that person. So the other thing I should differentiate, there's a difference between being pushy and being insulting. They're two clearly different things. You can be very tactful and pushy, and you could also be insulting. You have to make sure not to cross that line. And if you hit roadblocks, never accept defeat if you have the means to continue on. And so like in the US military, there's this code about, I will never surrender, yada, yada. Basically, to summarize it down, if you still have the means to fight, you are not allowed to surrender. And that applies to much more than just military situations. If you still have WBS number to charge to, if you still have procurement in your bank account, if you hit a roadblock, don't stop. If you still have the means to continue on, continue on. All right, and then the last thing, this is the group discussion part where we're going to learn from each other. And this is a wonderful quote from Einstein. So logic gets you from A to B, imagination will take you anywhere. And the big picture here is all of us at NASA are very good from like an analysis perspective, is sitting down and cranking out analysis. But you really have to work on what is, if you're surrounded by trees, can you see the forest? If you have a unique problem, do we want to go at it with the same sledgehammer we've always been going at it with? Or is there a way to circumvent that and come up with a unique solution to an existing problem? And so that's where we'll turn it over to group discussion, and I'm going to sit down like you all and stop talking.
So we have, we have two mics, and so hopefully we're recording this. That's why I really want you to use the mic if you're going to ask a question. And I'm not going to ask a question, but it's on. I'm not going to ask a question, but I'm going to compliment Bill because we had a team of students this past summer. There were 10 of them. They were from different disciplines. They came together to work on a project, and Bill was their technical advisor, and Dan helped too to make this happen. Dan, you want to wave to everybody? Dan is Bill's boss. He's his branch head. Anyway, so they were given a long list of things that they had to do, and it was for building a UAS from scratch, making it capable of package pickup and delivery, picking out a package from a group of other packages.
I basically tried to make it impossible, purposely.
Yeah, and so what happened was all these people at NASA started telling everybody, including the kids, hey, you'll never do this. This is ridiculous. This is impossible. You can't do it. They told Bill. They told me. They'd come in sessions with one of us saying, you guys are pushing these kids, way beyond their capabilities, blah, blah, blah. But we stayed positive. And Bill kind of made it simple for me that all these things have been done. They've just never been done collectively together in a unit, right? Something like that. So here's the short story. After 12 weeks, they not only had built the thing and flown the thing and demonstrated package delivery and package pickup and delivery, they also submitted 3 invention disclosures. And 2 of them have already been picked up for NASA partnership. The 3rd one we're still waiting on whether it gets picked up or not, but still, 2 is awesome. One was for the vehicle design, and the other one was for the package pickup and delivery mechanism. So in 12 weeks, this team of people that didn't know each other followed Bill's encouragement and his example, and we stayed positive the whole time, despite how many people were negative. And so what he's saying really does make a difference. And hopefully, because you guys are going to run into roadblocks your whole careers, no matter where you are, no matter if you're in industry or if you're here, or even sometimes just in your family life, when you have children, you have a teenager that doesn't want to cooperate. All these things can still apply. So hopefully you guys have some questions for Bill, and I'm going to pass this microphone down this way. Right? I know you have a question. That one works too.
All right, cool. So I got a question for Bill.
All right.
So you talked about how you decided to sacrifice some airplane performance to finally land on what would be the GL10 model. And part of the original project problem, you had said that there was this hopeful, idealized requirement to fly around for 24 hours. I'm pretty sure that wasn't like. That part was also shaved off for the plane too. How long was the GL10 able to fly around on its own?
Right. So great question. I should have been more specific. The aerodynamic efficiency of the GL10 design, basically the lift to drag ratio of that aircraft from a conceptual design perspective was coming out to 17. The previous models in the phase 2, those were getting lift to drag ratios of about 20. So one example of that is, and the way the design would still meet the 24-hour mission because we actually got a little bit better propulsion system. So we lost in aerodynamic efficiency, we gained in propulsion system efficiency. And the vehicle that you saw flying is all battery powered versus the conceptual design of the one for the other government agency would be a series electric hybrid and a much larger vehicle. So this one under battery power with a full load of batteries, if it takes off and immediately goes into wingborne flight, spends all its time in wingborne flight, which is a really short vertical landing, can fly 35 minutes.
That's pretty cool.
Yeah.
All right, and then so the conceptual design would probably do okay.
Yes.
Okay.
Yep.
Sweet.
Yep. And the other thing that was de-scoped was on this vehicle was since money was tight, our role was to demonstrate a feasible transition, and we de-scoped all the other requirements to try to save money.
Sounds cool.
Yeah.
Well.
But specifically, the performance we turned down was the wing plan form. Like on the previous vehicles, the wing was totally optimized to maximize L over D at the expense of handling characteristics. Like, for example, had a very strong taper ratio and not very much twist in the wing, versus the GL10 vehicle has a taper ratio of 0.7 and 3 degrees of washout built into it. So as you stall it, it doesn't have nearly as hard of a roll-off.
Okay. Next.
Cool. All right, quick afternoon.
Come on, you guys. I'm sure you have some
All right, what you got?
questions.
Talking about developing new things and breaking through the barriers of controls, were there any novel control methods that you developed to handle all the actuators, the control surfaces, motors? Because I'd be interested in that.
No, honestly, like all the feedback loops were PID, proportional integral derivative. And actually, they were all, we had integral control on like pitch and roll rate, which is effectively proportional control on pitch and roll angle. But yeah, just simple PID. Yeah. And then the controller we bought only had 8 outputs. So there's 10 motors, 9 control surfaces, wing tilt, tail tilt. So we gang stuff up. So all 4 motors on like the left wing are the same command. All 4 motors on the right wing the same command. 2 tail motors are the same command. The ailerons were ganged together to get it down, so we only had 8 outputs to work with from that controller. So
KK2 board?
yes. Yeah. Yeah.
Danny, can you give some perspective on what it's like from the other side? Like, you're the administrator, Bill, watching up. Some perspective on that?
Well, I would just say I'm one of many who supported Bill, and from the premise of approaching the bureaucracy or whatever and busting through, we want to do the same thing. So just realize that you're supported by a lot of people that want to help you, and it's that kind of environment that really is cool in NASA. So I would say that's what makes us unique.
Yeah, I've been blessed with very supportive management in SAC-D, so that was highly, highly helpful. Yeah. And when we ran out of money, they gave us more money too, which they put their money where their mouth is too. So that was appreciated.
You do cue in one thing that we did have to work through, which was the organizational side. Mm-hmm. And we had to get, essentially, this didn't come as a normal project, so we had to get a bunch of folks in the room and say, yes, we want to support this. All of us want to support this because we can't just have one organization do it all. Mm-hmm. So that was a key part. Yeah.
Yeah, it was really a cross-center team. So every organization was touched, from like ARD to process the money coming in, to ED to RD to even OHCM. Some of those folks helped with processing the WBS numbers, and so it touched everyone in the center from the model shop. They built it on center, did the detailed design on center. Wind tunnel test was done on center. So it was a good team across the center.
Jonathan has one.
Thank you, Dan. So this is clearly a success story for Langley, and that's very exciting for all of us. Are there any aspects of this project that if you had had just a little bit more money, you would have liked to have been able to demonstrate with this vehicle?
Yeah, probably just more performance. So like we got through that initial feasibility testing to show we could get through and show that, hey, this vehicle transitions, it flies around like an airplane. We never did get to do glide testing, to fly, get in a glide, to flight test, validate the drag puller in the airplane. And a lot of performance things we never got to. And hopefully, I'm no longer involved with the GL10 project, but the project is continuing on, and they'll put a hybrid range extender in it. They'll put autonomous control systems on it, and really sort of shake out the vehicle, as well as use the vehicle as a test bed for other technologies too. So it is kind of continuing on slowly. And we also, for an acoustic test, we flew it over and actually put the vehicle into a tree and did more damage to the vehicle getting it out of the tree. So it's actually getting repaired now too, which is why stuff hasn't happened in the recent history.
Bill, we have a couple of questions from Mark.
Okay.
How was the project affected over the timeline with various team sizes, wind tunnel testing, model building, flight testing, etc.? Were there times where things were moving too quickly or too slowly, and how did that change how you felt about the project as a whole?
Yeah, great question. Well, as Mark asked the question, Mark was intimately involved with the project. So in the flight testing program, he was one of the interns, and I gave him the job of keeping track of all like the data logging and keeping track of the data after every flight as we brought it off the vehicle. But at the peak, we had 12 people working on the project, and that's when everything was happening of the detailed design and fabrication starting. And then in the last little bit, it was only 3 of us to finish out. 3 of us plus 1 contractor. The pilot is an NIA contractor. So a total team of 4 actually did the flight testing. So that was the small side of the team.
How did it change how you felt about the project?
Oh.
Team size is changing.
Well, I would say the team size should be adjusted as the needs adjust too. So realistically, we actually did have a good team size to vary as the workload was going up and down. So actually the team size worked out well at the different phases. Yeah.
Can we go back to the slide where Mark was in the slide so people can see Mark?
Oh, sure.
I know he's going to appreciate that. He's at Johnson now. He's a Pathways intern at Johnson. But he worked here all last year. The guy with the toboggan, the orange toboggan, Mark, we're seeing you now. He worked with Bill and his colleague Dave North for 2 full semesters and most of the summer to help them do this. It was a great experience for him, one that he'll never forget.
Yeah, we put him to work. He put in extra hours beyond what he could bill.
They actually got to take this vehicle to the AUVSI conference in Atlanta, and it was a big hit because it's so cool looking when you see it. We've had it out here in the hallway.
Oh, it's outside right now? In the
Is it?
hallway?
No.
Oh.
Last year we had it out there in the
Oh,
hallway
gotcha.
before you guys went to AUVSI. So if you look up AUVSI, the national conference that happened in May, you can see the picture of it on display with a bunch of other NASA stuff. Are there any other students or people here that have questions? No, go ahead.
I actually was curious. You said, I'll wait. Yeah.
Thank you.
I was actually curious. You said as a lieutenant, obviously, when you were in the Marine Corps, that you were leading by example from a superior standpoint. And also with your students, you were doing the same. Have you had any experiences leading up? And maybe Dan could speak to that as he's leaving really quickly. No, but have you had any
Phil
experiences?
says I can't influence
Because-
the bosses. So.
But I think that
I'll let
is
Phil and
something.
Dan walk out and then I can answer.
Exactly, and that was,
You slide a couple Benjamins in at the right time. You know?
But I think that's a really important skill to have, or to at least attempt.
Right.
And I mean, it can be easy to lead down, but when you're leading up, especially as students or early career, so do you have advice in that area?
Yeah, I mean, honestly, think about it as the same thing. Whether it's a peer, a subordinate, or a superior, you have to figure out what motivates that person, figure out what you want to do, how that would motivate that person, and whether they're superior or a junior, it's actually the same interaction. So, like, the branch head needs to make sure a certain amount of work gets done in the branch, and things like that needs to make sure all the FTE's covered. And if you can go to the branch head, be like, hey, this is a project I want to do. It's going to bring good, like, publicity to the branch. And by the way, here I went and found that this person has WBS that they're not planning on using. And you put all those pieces in place on the table in front of them. They go, okay, go do it. So, yeah, it's still the same. Figure out what motivates them and show them don't say, I have a problem, what can I do? You come say, I have this problem, this is what I want to do, and I got A, B, and C, can I do it? And that's a lot easier for them to say yes. Yeah. What are some other, getting back to like what Einstein said, if we don't have other questions, I mean, what sort of barriers are there in our organization that are ones that are affecting you all, and ways we could possibly circumvent those or break those barriers or find an easier path through those barriers?
Entrenched culture. You know, we've always done it this way.
Yeah.
So
That I've heard that on more than one occasion. And it's frustrating to hear that. But, well, actually, what do you all think? What's the way to mitigate that? Is if you're trying to do some task and someone says to you, well, that's not the way we normally do it, how would you respond to that? Why? That's a good one. Yeah.
Because that's the way we've always done it.
Yeah. Yeah. Well, come on. Everyone's got ideas. How would you respond to that person?
But why won't this work?
So the way I would push back is I would ask a more specific reason. So you said we don't do it that way, we do it this way. And figure out the intent behind that person's statement. So I'm trying to think of an example of a process. I don't know, who cares what the process is, but the person works that facility or works that office and they have their normal process and say, this is the way we normally do it. So if you can understand the bigger picture intent of why they use that process, you can probably come up with a way that meets their bigger picture intent, which is what their real requirements are, and not necessarily, and adapt that process to fit your needs. So the reply back to them is you have to get an understanding, and I can't say it's particular phraseology, but you have to understand their reasoning behind why they use that process, and can you still meet that bigger picture intent with a slightly different process that accomplishes your needs? Yeah. Because realistically, we can't compromise safety. Like, for example, like with this Grease Lightning vehicle, we had to show that we're never going to hurt a person. And so we could take risk with the aircraft itself, but nobody was going to approve us to go fly if we were going to put a person at risk. So, I mean, all these, like in the case of the sorry, I'm beating up on the ASRB. They're a wonderful group and organization, and they have a very important place to ensure safety, but they are a very process-driven organization. And you get piled up in all these processes of how to get through ASRB, but really their big picture intent is to make sure you don't hurt people on center, because that's a safety issue, and that the project can match their risk associated with losing that vehicle to what their research need is. And so if you can maintain that higher level intent, and that's where the bit came, okay, well, let us prove to you using the GLARFs that we can show that this particular avionics hardware and this open source software works, then we got permission to go fly the bigger vehicle. So yeah, understand that bigger picture intent behind their process.
So none of you students have any questions? You're not running into any obstacles like trying to get your degree or working with your professors? None of that? I find that really hard to believe.
A comment, not a question. As someone who's had intern experiences in both private industry and here at NASA seems to have significantly more inertia than commercial space companies. Do you think this is a factor of our longer history, government restrictions, or even the older average workforce age? Understanding the root of the problem seems crucial.
I think it's a combination of all things. One thing to clarify first is like risk posture is a choice. So NASA in the 1960s when we went to the moon was willing to accept a very different risk posture than NASA is willing to accept today. And some things you can change, some things they are what they are. Like, for example, the military is willing to accept a very different risk posture than a civilian organization. And even the military has important safety needs, even in hazardous situations. So, like, a commander can't be, you can't have General Custer anymore in the U.S. military, where he said, where all those Indians come from? I mean, you need to know what you're going to do. You have to have a good understanding of what you're going to get into. So risk is a choice, and a lot of that comes from the choices that are made at the higher level and at the societal level. So, like, realistically, NASA can't have front page news of, hey, we killed NASA employees again, because that would be damaging probably to the, would eventually get tied into the NASA budget and cut the NASA budget. So in the case of a private company, they don't have nearly as many stakeholders to please as a governmental organization. So they can make those risk choices amongst a smaller circle of people, which enables them to have a different risk posture. All right. Well, should we call it an afternoon there? Sure. Tell them to come back and visit Virginia. Absolutely.
Do you guys, I just want a show of hands. I mean, did you think this information was new to you? Have you heard this before? Show of hands, how many people learned something new? Okay, well, it was worth it in that respect.
Cool.
I mean, I can cite so many examples just from my own life where you have to apply all these principles that Bill has discussed. So hopefully you'll remember them. You guys are fairly young now, but you're going to have many, many opportunities to come up to people that are going to tell you no. Yeah. Even when it's trying to change a major or get your dissertation subject or your thesis subject or any of that stuff. Yeah, and you're going to have to learn to push back and to stand up for yourself and try to find civil, polite ways to show them that you can do it a different way.
I think that's the point, is the civil, polite, knowing your audience and their intent. Okay, I believe that that's the important part, is civil, polite, knowing your audience, knowing their intent, a win-win for everyone. Yeah. I think there is, so one of the things, and I come from a social sciences background, but one of the things that when my kids are in college now, and I told them each, I don't care what you major in, take some psychology classes, get to know people so that you can be a team member or a team leader and know, how to, because engineers, I mean, a lot of that, and I have to take engineering classes so I can talk to them, but no. But I think that knowing your audience and knowing what the end result is and keeping that in mind instead of just getting the pushback, knowing we're all working towards the same thing. So we've always done it this way. That's what you're hearing all the time, and that's your barrier. But knowing that we're still trying to all get there, and finding that common ground. I think that's really important.
Yeah. Yeah.
Well, if you guys have any other feedback to give us on this seminar series, please send us an email or something. You can send it anonymously if you want, but depending on what email you use, you'll probably be discovered unless you use a non-NASA email. But seriously, I mean, we want to make these seminar series useful to you and to your careers. We're targeting young people, obviously, but I mean, it's applicable to people that have been here for 30 years, too. So, because there's a lot of people that just accept no for an answer, and then they feel defeated, or they just think that their ideas weren't worth anything. I mean, that's not the right mindset. So hopefully we'll continue on this course of teaching you guys something new and a different way to think of things. And Bill, I can't thank you enough for taking your time to do this. Cool. Thank you so much for agreeing to it.
You're welcome. Yeah.